Hi everyone, this is Professor Matt Turner with Purdue Polytechnic, and this is a video lecture for ECET 364, and today we're going to talk a little bit about vector notation. This is just to kind of get our math skills up to par before we get into our discussion of electro and magnetostatics. Today what we're going to do is we're going to look at how we describe the distance between 2 points in space using vector notation and talk about how vectors are utilized in electromagnetics. We are going to discuss and calculate the concept of a unit vector. We're going to perform some simple arithmetic using vector numbers, and this largely is addition and 3 types of vector multiplication. And finally, we're going to review the fact that there's multiple coordinate systems in the world. The rectangular or Cartesian system is just one of those, and we're going to explore 2 more, the spherical and the cylindrical coordinate systems. So let's dig in today by just discussing what vector quantities are. And most of the quantities that we are used to dealing with in the world are scalar quantities. And by scalar, we mean that they represent by a single number. So if I ask you how long the distance from point A to point B is, typically you would give me a length in meters. Or if I ask you how long did it take you to drive to work, you would give me a time in units of seconds. And those are scalar numbers. They're represented by a single number. A scalar field is a representation or a mapping of a scalar quantity as it varies with position. And so here what I'm showing is a topographical map, and a topographical map represents a flat, or represents a space like the surface of the Earth, and it's projected onto a flat plane with a y-axis and an x-axis. And in this plot, continuous lines, we see that there are these continuous lines. Here's one, there's one, and they represent points of equal elevation. So if I were to plot, or if I were to just go out to the real world and look at how high the geographical features of the Earth were at this location in XY space, I would see that, you know, it's got a certain height associated with it. And topographical maps, the line itself doesn't actually represent height. The spacing of the lines represents height, but the lines represent equal distance. And the point here, though, that's important for electromagnetics is that this is a scalar quantity because the line, the continuous line, only gives you one piece of information, which is the altitude of the surface geometry. In electromagnetics, we're going to often be dealing with vector quantities, which mean that the quantities have a magnitude and a direction. So, for example, gravity has a magnitude, which is how strong the attraction to Earth is, and it also has a direction, which is that you get pulled towards the Earth. So gravity has a strength associated with it, a magnitude, and it pulls you towards it, which is its direction. A vector field is like a scalar field, but it has direction associated with it. So a vector field is a picture of how vectors are mapped onto space. So I've got a picture of a vector field here, and this would be a 2D gravitational field plot. So here we've got some sort of mass inside of the plot, and at any point in XY space, I've plotted 2 pieces of information. The length of the arrow indicates field strength, how strongly you're pulled towards the mass at the center, and the orientation of the arrow tells you which direction the force is going to act in. So if I'm right to the immediate right of the mass, I'm going to be pulled strongly to the left. If I'm to the left of the mass, I'm going to be pulled strongly to the right. If I am far to the right of the mass, I'm going to be pulled weakly to the left, etc., etc. So we see that these arrows, they have a size, which is their magnitude, and then they've got their direction, which is, in this case, you know, we see pointing down and left. Here it's pointing up and left, etc. So it gives you an idea of what we mean by a vector, a quantity with both a magnitude and a direction. So before we create vectors, or before we start describing physical forces and properties in terms of vectors, we have to be able to define the location of points in space. And in the maps I showed you, we did that in 2-dimensional space, but in this class we're going to extend that into 3-dimensional space. And so typically we've done this in the past using what we call the Cartesian or rectangular coordinate system. So just to kind of be formal about it, the Cartesian system divides 3-dimensional space into 3 mutually orthogonal axes. We've got the x-axis, the y-axis, and the z-axis. The location of any point in space is then defined in terms of its distance away from each of the axes, typically listed in order of x, y, and then z. So for example, I could define the point P, which is at 1, 2, 3, and what this means is that the point P is the location in space that is 1 meter along the x-axis, 2 meters along the y-axis, and 3 meters along the z-axis. So you'll note that the combination of these 3 points in the Cartesian systems creates a unique number that identifies only one point. I can't have 2 different numbers that result in me being in the same point in space in the rectangular system. In addition to the rectangular or Cartesian system, there are 2 other major coordinate systems that are often used by engineers and physicists and mathematicians, and these are the cylindrical coordinate system and the spherical coordinate system. In the cylindrical system, any point can be visualized as existing on the surface of a cylinder, and that's going to have a unique height, a unique radius, and a unique angle. In this diagram, what I'm showing is that in the cylindrical coordinate system, any point P is defined as r, which is the radius of the cylinder, theta, which is the angle of the point as measured from the positive x-axis, and z, which is the height to the point along the cylinder. Note that r and z are both length measurements, and theta is not. In this coordinate system, theta is going to be measured in either degrees or radians since it's an angle, and it can have units from 0 to 360 degrees. In the spherical coordinate system, a point is visualized as existing on the surface of a sphere, and it has a unique radius of the sphere, and it has 2 angular rotations, theta and phi. In this diagram, we can see that r is just the radius of the sphere, theta is the angular rotation as measured from the positive z-axis, and phi the angular rotation as measured from the positive x-axis. Cylindrical and spherical coordinate systems are not as common as the Cartesian or rectangular coordinate system, but they're often used to make mathematical calculations in electrostatics and magnetostatics and in antennas they're just easier to perform in one of these other coordinate systems than they are in rectangular. So we'll use them largely as a method to make our math a little bit simpler.